In this video, we're going to discuss logistic growth. Our logistic growth equation is I of t equals k in the numerator, 1 plus k minus I0 over I0, e to the negative RLT. K is a maximum infected population. That can be sometimes hard to assess. In this case, we'll just assume we know it. I0 equals number infected at time t equals 0. That's the initial number infected. RL is a growth constant. We put an L here to indicate logistic. And then t equals time in days. I of t is a number infected at time t. This gives us what's sometimes called an S-curve. We start at t equals 0 when initial infection number I0, there's a maximum, and it escalates. It reaches what's called an inflection point right here, and then it levels off. It never surpasses the maximum number infected. So for instance, let's suppose on January 10th we have 20 infected, January 15th, 5 days later, 40. The infected population doubles, and the maximum infected population is 200. Assume we're on an island and everybody's going to get it, and there's 200 people on the island, and whatever infection's going around. That's a simple scenario. Let's set up a logistic model. First of all, we have to identify a few variables. If we can identify these variables at the start, k is equal to 200, and I0 is equal to 20. And so what we're going to do is plug in 200, 200, 20, and 20, and we'll simplify the model considerably right in the beginning. I of t is equal to 200 divided by 1 plus 200 minus 20 over 20 e to the minus RLT. And we can compute this, 200 minus 20, 180 over 20 is 9. This whole fraction here is really just 9, so we're going to replace that. If these are odd numbers, of course, you can do that on a calculator. 1 plus 9 e to the minus RLT. This here is a decay factor. As time goes on, this decays to 0. And then 9 times 0 is 0. And the infected population tends toward 200 divided by 1, which is 200. Now the only question is, how do we find RL? Well, we have this second data point right here. In 5 days, t equals 5 days, I is equal to 40. So the math is a little bit tricky, but we'll go over it, and that's why we're here. We can plug in 40 for I, and then we have 200 over 1 plus 9 e to the minus RL times 5. Now the question is, how do we get that RL? You can write this over 1, and then we're going to cross multiply, get rid of the fractions. And let me clear a space here. If you cross multiply, we can keep this 40 actually before we multiply. 1 plus 9 e to the minus RL 5, and that's equal to 1 times 200, which is 200. Now you can distribute, but 40 goes into 200, so in this case it's just as easy to divide it out. And we got 1 plus 9 e to the minus RL times 5 is equal to 5. 200 over 40 is 5. Subtract 1. 9e to the minus RL 5 is equal to 4. Divide by 9. This is just basic math. E to the minus RL times 5 is equal to 4/9. And we kind of ran out of room there, but that's okay. Let's bring that up here. E to the minus RL times 5 is equal to 4/9. Of course, we're going to get rid of E by taking the natural log of all sides. Natural log of E to the negative RL times 5 is natural log 4/9. And it cancels that out. Minus RL times 5 is ln times ln of 4/9. And you can divide by -5. Divide by -5. That gives you RL is equal to ln 4/9 over -5. And we can approximate that. Let me get a decimal approximation for that. It looks like we have, take 0.162 to 3 significant figures. Okay, our goal was to put that back into our logistic equation. I erased part of that, but in any event, we have I of t is equal to 200 over 1 plus 9 e to the negative 0.162 t. And there's our model. There's our logistic model. So we'll have a subsequent video where we'll learn how to work with that equation. But for now, that's how we produce it. A lot of good math, good algebra, and that's all for this video.